Consider this container. You can take this as a beaker also containing water. You got the upper surface of the water. Since the beaker is cylindrical, this upper surface of water is circular. So when it is circular, now let me assume an imaginary line AB. Now there will be forces acting on the horizontal area. Suppose if you take this AB as a hypothetical line, there will be two opposing forces. They are stretching the entire surface. So this is the force acting on the entire top surface of the liquid, in this case water. So this is not to be confused with the intermolecular distance. It is nothing but the line acting along the surface acting forces is applied. This is the case with the soap bubble. In developing the soap bubble, we used to play with some circular ring or in this case a horizontal loop. The horizontal loop is PQRS. Now you can find this QR. This QR rod is movable to a new position Q dash R dash. So thereby you can change the area. Do you understand this? Therefore, the QR, the rod QR, is moved on the right side to the new position Q dash R dash. Since the soap film, it has the top surface and the bottom surface. So that is why I have used here 2L. Do you understand this? So 2L means you have got the two surface area. That is, actually, this is twice the surface area into the length factor. When you consider a beaker, particularly containing water, the L is nothing but the length of contact line between water and solid boundary you are considering. For example, in the case of beaker wall meniscus, you know pretty well that it is nothing but the circumference, that is inner circumference. So that inner circumference where the liquid and the inner wall of the beaker, they have the common contact. So along the 2 pi r, the L acts, that is this surface tension acts. Let me assume I am having a plastic, that is a balloon layer, a balloon skin. Now it has to be applied circumferentially on a tube so that you can have a flat surface. Just by stretching on one side, can you get a flat surface? It's ruled out. You have to apply this force circumferentially in all directions. Do you understand? So that you can form a neat stretched balloon film on the cylinder. Okay, so something like that. The surface tension also occurs along the boundary line of the container where the liquid is kept. In the case of beaker, what happens here along the inner circumference at the meniscus. What do you mean by meniscus? That is the contact point of this liquid, that is water, with the inner wall of the beaker. So that is why this L is taken as the circumference, that is 2 pi r. I hope now it is very, very clear. But in the case of formation of soap film in rectangular frame, I am stretching on one side only, that is PQ. So that PQ is taken as the L. Do you know why? Because I am stretching on that side only. Okay. And that is why I had taken L. But you may wonder why I have taken 2L, because this soap film has two surfaces, top surface, bottom surface. Even though it may be very, very thin, but it has got two surfaces. So we need to consider the stretching line as the twice, that is one for each surface. So the upper surface is stretched by L, the lower surface of the film stretched by another L, and that is why I had taken PQ as, in the case of soap film, 2L. I hope now it must be very, very clear to you. This problem is based on the topic surface tension in class 11 physics. Two liquid drops of radii 1 mm and 2 mm coalesce. Its surface tension is 0.07 Newton per meter. The energy released is closest to. They are given four options, out of which the first option, that is 5.9 into 10 power minus 7 joule, is the correct answer. Let us discuss how this problem can be solved. Before discussing the problem, let us try to understand the concept behind this. The energy released on coalescence of liquid drops. Coalesce means merging of liquid drops. When two small liquid drops merge, that is coalesce, to form a single large drop, the total surface area increases because the surface to volume ratio reduces. Since surface energy is directly proportional to the surface area, this reduction leads to a release of surface energy in the form of heat or kinetic energy. Let us try to derive this surface energy. Each group has a surface energy. So that is given as the surface tension into surface area. That is area of the drop, total surface area of the drop. S represents the surface tension that is given in Newton per meter. A represents the surface area of the drop. Since the drop is spherical, its surface area is 4 pi r square. Therefore, for two drops, we have to calculate the surface energy as EI is equal to 4 pi s of R1 square plus R2 square. That is 4 pi s R1 square plus 4 pi s R2 square. Since 4 pi s is common, I had taken outside the bracket. Therefore, 4 pi s R1 square plus R2 square, where R1 and R2 are the radii of two drops, which are coalescing, that is mixing, to form a large sphere or drop. After this coalescence, that is the mixing of these two or more drops, one large drop of radius or is formed. It means the volume is conserved. So the volume of a bigger drop, that is 4 by 3 pi into R cube, that is capital R cube, that represents the total volume. that is the bigger volume, that is equal to the sum of the volumes of individual bubbles. So bubbles in this case drops. That is a 4 by 3 pi r1 cube plus 4 by 3 pi r2 cube, where 4 by 3 pi is taken as common. Therefore, 4 by 3 pi into r1 cube plus r2 cube. Therefore, R is equal to, now this 4 by 3 can be cancelled. And that is why R is equal to R1 cube plus R2 cube whole power 1 by 3. Because R cube is equal to R1 cube plus R2 cube. We want R. Therefore, taking cube root on both sides, you are able to get R is equal to sum of cubes of the individual radii, that is the radii of individual spheres. So that is why we put R1 cube plus R2 cube whole power 1 by 3, right? Therefore, the surface energy of the new drop now is EF is equal to 4 pi into S R squared, where S that remains same, nothing but the surface tension. But the R is here a bigger one. So the radius of the newly formed drop. Now let us talk about the energy released and let us try to do some numerical examples by substituting the parameters in the given equation of energy released. The decrease in energy is equal to the energy released. Therefore, delta E is equal to EI minus EF, that is energy in the initial level minus energy in the final level. When I say energy in the initial level means that is energy associated with the two drops, and the energy final means once these two drops are mixed to form a bigger drop, and that is EF. Therefore, 4 pi s, that is common, of R1 squared plus R2 squared minus capital R squared. Whereas this 4 pi s of R1 squared plus R2 squared represents the energy I, initial energy. And 4 pi s of R squared, capital R squared, that represents the final energy. So since 4 pi s is common, I have taken totally outside the bracket. Therefore, delta E is equal to 4 pi s into R1 squared plus R2 squared minus capital R squared. Now, let us proceed with the example problem here. So, in the problem given, the parameters are R1, R2, then surface tension. So, the radius of the first drop is 1 mm. That should be converted into meter. Therefore, 1 millimeter means 1 into 10 power minus 3 meter. R2, 2 millimeter. That is 2 into 10 power minus 3 meter. Yes, surface tension. That is equal to 0.07 Newton per meter. Let us now compute the R, the capital R, that is the radius of the new sphere, new large sphere, is equal to R1 cube plus R2 cube whole power 1 by 3. So 1 cube plus 2 cube. 2 cube means 8. So 1 plus 8, that is 9 power 1 by 3 into 10 power minus 3. That works out to 2.08 into 10 power minus 3 meter. Now let us substitute in the energy equation. So delta E is equal to 4 pi into the surface tension, that is 0.07 into, and you have got these values, is it not? So you can simply replace this, and finally you are able to get 5.9 into 10 power minus 7 joule. So this is the way to calculate the energy of the newly formed sphere because of the surface tension. Now let us try to interpret from these concept and problems. The merged drop has less total surface area. Secondly, the difference in surface energy due to reduced surface area appears to be released energy. And therefore, here the energy release is equal to decrease in surface area and multiplied by surface tension. So let us try to understand the key insight of this entire concept. Smaller drops have higher surface area per unit volume. It means higher surface energy. When they combine into a larger drop, the surface area reduces. That is, the surface energy decreases. Hence, the energy is released during the combination of drops. Here I have given the saitechinfo worksheet. Energy released when two liquids, that is, liquid drops coalesce, mix. This is an interactive calculator. You can find the step by step derivation, and all the units are given in SI. Now, the radius of first drop is 1 mm. The radius of second drop is 2 mm. Now, the surface tension is 0.07 Newton per meter. So, these are the given parameters, and we have to find out the energy associated with that. So, the energy associated with this is found to be, we already calculated, that is 5.92 into 10 power minus 7 joule. Now, here I have given the, that is step by step approach for this. So the given parameter R1, the radius 1 mm, another parameter that is R2 is 2 mm, and S is equal to 0.07 Newton per meter. So the first thing is you have to convert the millimeter to meter. So here I have converted, that is 1 millimeter is equal to 1 into 10 power minus 3 meter. When I put e power means 10 exponential term, that is 10 power minus 3 meter. And R2 is 2 into 10 power minus 3 meter. So this is expressed as 2 into exponentially minus 3 meter means 2 into 10 power minus 3 meter. Now the volume conservation gives the final radius. So R is equal to R1 cube plus R2 cube whole power 1 by 3. And now we have got the result of this R by substituting this R1 and R2. We are able to get 2.08 into 10 power minus 3 meter. Initial and final areas. Initial area is 6.2 into 28 into 10 power minus 5 square meter. But after mixing up, the surface area is found to be 5.4 into 10 power minus 5. Now you can find the difference between these two areas. Initial area was 6, but here it is 5.4. This is 6.3, this is 5.4. It means there is a decrease in area by the fusion of these two drops. Now the energy released, and that is why energy is released because the surface area is decreased. So delta E is equal to S into AI minus AF, that is equal to 4 pi S into R1 square plus R2 square minus capital R square. So from this we can calculate 5.9 into 10 power minus 7 joules as the decrease in energy, surface energy. Okay. Now the theory part is, that is the volume is conserved. That is the bigger volume 4 by 3 pi r cube, and here the total volume. But the surface area is reduced here. And that is why, because of the reduced surface area, there is a decrease in energy also. So that's what we have done here. Okay. So now we can have new problems also. You can try with the new problems by generating, for example, you can generate a new problem like this. Two liquid drops of radii 1.51 mm and 1.201 coalesce. If surface tension is 0.058, then estimate the energy released. Now you can try like this. and you can substitute these values and get the correct answer also, and you can verify. And this will generate again another new problem, again another new problem, again another new problem. So likewise, till you get exhausted and get quite conversant with this small, that is a concept, you can do it. And you can compute here also. And see, now I have given 0.507 as the drop, one radius, and another drop is a 2, and the surface tension is a zero point 0.8. So now the energy is this much. That is compute the energy we are able to get. Now we can reset the values also and randomize. So you can get enormous questions from here so that you can practice very well with this wonderful interactive workshop. You can develop your own questions and you can do it and you can verify it. Thank you very much.